So finally, we're going to take a look at the implications of having negative weights in directed weighted graphs. So the first thing to notice is that the easy solutions don't work at all. Dijkstra's algorithm just doesn't work in the presence of negative weights. So say this weight from 2 to 3 is -9. What Dijkstra's algorithm will do is just immediately select vertex 3 and never revisit that decision, saying the shortest way to get from 0 to 3 is to take this edge 0, 3, which has weight 2. But the actual shortest path goes over to 4, and then over to 1, and down to 2 for a weight of 10, and then the -9 makes it 1. So there's a way to get from 0 to 3 with path weight just 1 because of the -9, but Dijkstra's algorithm won't find that. So that's not going to work. And you might think, well, why don't we just make all the weights positive by adding 9 to everything? Well, that's not going to work because a longer path will have 9 added to it a lot of times, so it's just not any relation between shortest paths in this graph and shortest paths in that graph. So those easy attempts just don't work for dealing with negative weights in general graphs. So the conclusion is we need some different algorithm. And the topological sort one isn't going to work because the graph might have a cycle in it. So there's no topological sort. So we need some different algorithm. And the main thing to think about in terms of weighted directed graphs that might have cycles is that you can have this situation called a negative cycle. So this is a graph, it all looks fine, it's just got this one negative edge from 5 to 4 of weight minus 0.66. And these other ones are 0.37 plus 28, so this plus 0.65. But if you go from 5 to 4 to 7 to 5, then the distance around that is minus 0.01. And if we're trying to find, say, a shortest path from 0 to 6, well, as soon as you hit this cycle, if you really want the shortest path, what you could do is spin around this, well, an infinite number of times. You can make the path as short as you want if you hit a negative cycle. So negative cycles definitely can get in the way of trying to solve the shortest path problem. It makes it somewhat ill-specified. So the first thing is, if there's no negative cycles, then there's a shortest path tree. And if there's a shortest path tree, there's no negative cycles, assuming that you can actually get to the vertices. So what we'll want is graphs that have no negative cycles, and then we can work with those. And there's an algorithm, an old algorithm known as the Bellman-Ford algorithm that does the job. It's only slightly more specific than the generic algorithm that we gave before. It just says, so if you have V vertices, for just V times, all you do is go through all the edges in the graph and relax each edge. So you make V passes through, relaxing all the edges in the graph. And that's an algorithm that finds shortest paths in graphs that don't have any negative cycles. If there's a negative cycle, we'll talk about what happens in a minute. So let's look at that one in terms of a demo. So we'll just take the list of edges in the graph, and it could be in any order, and just relax them all. So to start out, we set the distance to the source 0 and everybody else's distance infinity as usual. And then here's the list of edges, so we'll relax. In this case, we start out with the edges sort of in the order that you'd get them by walking through the whole graph, so you get all the edges associated with each vertex together. So we relax 0, 1, relax 0, 4, relax 0, 7. That's kind of the way Dijkstra would start out. And then we go ahead and relax the edges that come out from 1. So 1, 2 takes us to 2 for the first time. 1, 3 takes us to 3 for the first time. 1, 7 is no help, so we ignore it. Now we relax, oh, sorry, I went too far. 2, 3 and 2, 6, and those that one takes us to 6 for the first time. And now 3, 6, that does not give us a better way to 6, so we ignore it. Now we go to 4, 5, that takes us to 5 for the first time. 4, 6, well, we could get to 4 and 9 and then 20 to 6, so that's no help. 4, 5, that's no help. Now we do the ones from 5, 5, 2. That's going to give a better way to 2, so that we improve that. And 5, 6 is going to give a better way to 6. Now 7, 5, that's no help. And 7, 2 is no help. So we've completed the first pass. And now we're just going to go through and relax all the edges again. Now a lot of them are really just what we did before, so they're not going to improve anything, like the ones at the beginning are not going to improve anything. But before too long, so still no improvement. But here, now the second time we relax 2, 3, it gives us a better way to get to 3. In the first pass that didn't help us, but second pass we relaxed 2, 3 to get us to 3 and 17. Now that's going to change things for 3. If we had already been through 3, it wouldn't matter. In this, we didn't take another pass to deal with, but in this case we're going to be coming through 3 later. Or there's another 2 to 6 gets better, and then 3 to 6, 2 to 6 beat it, so it doesn't help. And now I think there's nothing else that helps in this example. And in fact, there's no further changes. Once we have the shortest path tree, which we know from this example because it's similar to one that we did before, then there's going to be no changes to it. You're not going to find any edges that successfully relax. And so go through and try them all, and in the end we have a shortest path tree. So that's an example of the Bellman-Ford algorithm on a simple sample graph. Here's the visualization of the Bellman-Ford algorithm running on a bigger graph. And here's what it looks like after 4 passes, 7, 10, 13. And this graph has 100-some vertices, and it finds the tree in a relatively small number of passes. And we'll talk about the performance in a second. One thing is to be sure that the algorithm works. And there's a couple of ways to prove it. And again, the reason the proof has to be done with care is that there could be edges with negative weights, but no negative cycles. And the idea of the proof is that after you've done the ith pass, you've found the shortest paths containing at most I edges. And we'll leave that proof for the book. Now, there is a couple of ways to improve the Bellman-Ford algorithm in practice. And the most important one is that if you didn't change the distance to a vertex during one pass, then you don't have to worry about it in the next path. You don't have to worry about its edges in the next pass. And so what we do in practice is to just maintain a queue of the vertices that we found shorter paths to in each pass. We want to make sure that we keep at most one copy of each vertex on the queue. Otherwise, you could wind up with situations where the size of the queue blows up. But that's easy to do with a vertex indexed array to keep track of that. And so in the worst case, you could have all the vertices on the Q and then therefore all the edges relaxed in every one of the V passes. But in practice, not too many vertices really get relaxed. So this is a quick summary of the algorithms that we've looked for shortest paths. And we didn't do the code for Bellman-Ford. We've done enough code today. It's quite simple code that you find in the book or on the book site. So probably the simplest algorithm is when there are no directed cycles. And that's when we just topologically sort the vertices and then go through that list and relax every edge. So that's linear time. You relax all the edges in the graph and that's it. And that works even if there are negative weights. If there's no negative weights, but there may be cycles, then Dijkstra's algorithm works. And then we looked at E log V algorithms are slightly faster depending on what kind of heap you use. The Bellman-Ford algorithm, which works with negative weights as long as there's no negative cycles, if you do the Q, you can get in practice, it turns out to be linear time for the kinds of graphs that arise in practice. Although in principle, in the worst case, it could be E times V, which is much too slow. So directed cycles make the problem harder. You needed Dijkstra instead of topological sort. Negative weights definitely make the problem harder because you might need to get the worst case of Bellman-Ford. And negative cycles, in the presence of negative cycles, it actually makes the problem intractable. And we'll talk about that a little bit at the end of the course. One thing that you can do with the Bellman-Ford algorithm is to at least find out if there's a negative cycle. And one practical reason to do that is maybe it has something to do with something ill-specified in the problem. And so if you can detect a negative cycle and deal with it, that would be useful. And we'll look at another important practical reason for finding negative cycles in just a second. So anyway, since it's a useful thing to do, we're going to add two methods to the API, and that is, does the graph have a negative cycle? And then an iterable, if it does have a negative cycle, please give it to me. So for this graph, it would return true, and then it would give an iterable that would have these three edges that give me the negative cycle. So the observation, or the way to find a negative cycle, is to realize that what will happen with Bellman-Ford algorithm, if there's a negative cycle, is that it'll every pass through, it'll basically go around the cycle. Well, not every pass in the length of the cycle. It'll get stuck in a loop going around the cycle, depending on the order of the vertices. And it'll update and just get stuck going around the cycle. So by testing what happens after Bellman-Ford is done, even if there's negative cycles present, we can find the negative cycles. And that, in fact, if some vertex is updated in the last phase of the Bellman-Ford algorithm, then there's a negative cycle. And not only that, edge 2V is the last edge on that cycle. That's the way you got to V, and you can trace back to find the cycle. So just run the Bellman-Ford algorithm, and if some vertex get updated the last time through, it means that there's a negative cycle. In practice, actually, you don't have to wait till the last phase. You can check the dist2 entries for negative cycles more frequently. But anyway, it's possible to find a negative cycle. And let's look at an application. This is an application that it really motivates some people to understand shortest path algorithms. And the idea is currency exchange. And so these are typical numbers that you might see in a newspaper table, or nowadays in an app on your mobile device. that gives the exchange rates for various currencies. To convert a dollar to euros, use a factor of 0.741 and compute euros to Great Britain pounds 0.888 and so forth. So this table is a table of exchange rates. And the problem is there an arbitrage opportunity? So what is arbitrage? Well, arbitrage is when just by making exchanges according to the legal rates in the table, you can make money. So say we had $1,000 and then these are the going rates. Well, we can convert that $1,000 into 741 euros. So now, if we take those 71 euros and convert them into Canadian dollars, it works out that we get 1,012.206 Canadian dollars. And if we take those Canadian dollars and convert them back to US dollars, it works out that we have $1,007. Well, that's arbitrage, and that's interesting. If we could go ahead and do that for, well, let's say $10,000, then we'd make $70 on the deal, or $100,000 would make $700, or maybe $1 million would make $7,000, or maybe $1 billion would make $7 million. No reason to stop there. With arbitrage opportunity, you're making money off the system. So of course there's intense interest in looking for opportunities like this. Of course, in modern financial markets, there's many more things you can trade than currencies, and these tables are big and complex, and the market is supposed to take care of eliminating these opportunities, but if you're using a computer and you've got a fast algorithm for finding negative cycles in directed graphs, then maybe you can find the opportunity and take advantage of it before the market. So let's look at how it works. What we do is, again, model the situation with a graph. So we're going to have a vertex for every currency, and then an edge corresponding to every transaction or every entry in the table. So this is actually a complete directed graph, and the weight is equal to the exchange rate. And what we're trying to find is a directed cycle whose product of edge weights is greater than 1. So that doesn't look like a shortest path problem, although it's close, and actually it's very close. To convert this to a shortest paths problem, what we want to do is just take logs. If instead of using the exchange rate, we take minus the log of the exchange rate, and then multiplying turns to addition. If we're looking for multiplying the exchange rates, that's the same as summing the logs. And we took minus log, it means that what we're looking for, and when we're trying to find product bigger than 1, we're looking for a directed cycle whose sum of edge weights is less than 0. Find a directed cycle whose sum of edge weights is less than 0 in a complete digraph. That's the negative cycle detection problem, and we just saw that we can do that with the Bellman-Ford algorithm. And again, in a huge directed graph in a modern trading situation, that's an extraordinarily valuable algorithm, and you can believe that there are people out there running these algorithms in order to detect and take advantage of arbitrage opportunities. And if you don't have a fast algorithm, if you're using a slow one, it'll be gone before you can take advantage of it. That's a fine example of the value of building efficient algorithms for practical problems. So here's our summary of shortest paths today. We've seen some great classic algorithms that are important and extraordinarily useful. First one is Dijkstra's algorithm, which is a fine, efficient workhorse algorithm that you see used every day. And it's a graph search algorithm that is similar to Prim's depth first search and breadth first search that we've seen before and we'll see again. If the graphs have no cycles, which is a situation that arises in several important applications, we can do better than Dijkstra's algorithm. It's easier, and also negative weights are no problem, which enables us to solve scheduling problems in other examples. If there's negative weights and negative cycles, we can detect negative cycles, and if there aren't any negative cycles, we can find shortest paths. The general problem is intractable, and we'll come back to that. But the key point that I want people to remember from today's lecture is that shortest paths is our first real example of a general problem-solving model where there's a lot of important practical problems that we can cast as shortest paths problems, number one, and number two, we have fast solutions to those problems with these classic algorithms that we've talked about today.